Hello everyone, hope you all are doing great. Welcome to this video on how to play with 2D convolution. We are going to be looking at how to convolve images with some of the specific matrices that blur the image, sharpen it, brighten it, or move the image. And this method or this algorithm or this way of programming is used by applications such as Instagram or Snapchat or any other application that has their own filter to edit their image. So let's have a look. So let's get started. Here's our MATLAB window. Make sure that the directory of MATLAB has that image that you want to be processing. So let's start with it. To import an image into MATLAB, first of all, we'll need to type in a variable. I'm calling it I, and you'll need to type in the function which is imread, stands for image read, and in apostrophes you'll have to type in the name of the image. My image name is images.jpg. There the image gets loaded, and if you want to see the image, you just type in imshow, that is image show, and type in the name of the variable that you have stored the image in. There, the image comes in. I have chosen the image of a cat, and the reason I've chosen a black and white one is that this demonstration is going to be on black and white, but on Google the images that you find are actually RGB. So even though as you find images that are completely black and white, you will need to be converting them into grayscale, because convolving RGB images is like convolving three-dimensional signals instead of two-dimensional signals, because red is one of the signals or one of the images, green is another image, and blue is another image. So I'll be doing this demonstration for black and white or grayscale, but you can apply the same logic for RGB, in which the image has to be first converted into three different images: red, green, and blue. And then you do the convolution for each of the sections and then combine them to form the RGB image or the processed RGB image again. So firstly, I'm going to show you how to find the dimensions of the image and why I was saying that RGB part is present in the black and white images that you download from Google. So for that, you type in the function imfinfo, and then you type in the image name again in apostrophes. There it is. So as you can see over here that the width of the image is 275 and the height is 183, which means that the image has a resolution of 275 times 183, and the number of samples, since over here it says there are 3, it means that the image is RGB. So we'll need to be converting that into grayscale, and in order to convert that into grayscale, we'll type in the function RGB to gray and the image. There it is. The image has now been converted into grayscale. Secondly, if you look at it in the terms of a matrix, then the image is a matrix having 275 columns and 183 rows. And if it were to be a one-dimensional signal, then the image would have had 275 samples. So that's our image. Now coming on to the new screen so that we can begin our image processing. So welcome to the new screen, or the cleared screen as I should say. I've already made a few of those matrices and I'll show you their values. For example, in order to move an image a pixel upwards, the matrix it has to be convolved with is this one, and in order to move it to the right and to the left. So if you look at these matrices, in order to move an image a pixel up, down, left or right, the image has to be convolved with a matrix having a unit value in the opposite direction from where it has to be moved from the center. For example, if it has to be moved upwards, a 1 has to be placed in the central column in the bottom row, and if it has to be moved to the right, a 1 has to be placed in the leftmost column in the central row, and if to the left, then 1 has to be placed in the central row in the rightmost column. Similarly, for down, it will look something like this. So, and the matrices that blur an image look something like this, and this, and even this. So, if you look at this matrix, what it does is it moves the image to the left and it moves it up simultaneously. And doing that simultaneously, it causes a blur. This matrix, it moves it down, up, right, and left, simultaneously causing a blur in the image. And if you imagine a real life scenario, then an image gets blurred when our hands are shaky and are constantly moving and are not, stable. Or we get blurred images when our object is moving really fast, so fast that we are not able to have our camera lenses stationary relative to that object. So here are three examples of blurring matrices. One is two of them are 3 by 3, one of them is a 5 by 5 matrix. The first one causes the lowest blur, the second one causes a much better blur, and the third one has the most blurring effect. The reason is, well, if you're familiar with statistics, then you've heard of the Gaussian bell-shaped curve, and what it has a standard deviation, and the standard deviation of blur number 3 is 1. It has the largest standard deviation compared to the previous two, so it will be having the largest blur. And talking about the size of matrices, 3 by 3 matrices and 5 by 5 matrices are generally used for image processing, and GIMP used to use 3 by 3 and 5 by 5 matrices for editing images and blurring them and sharpening them. So no matter what the resolution of the image, 3 by 3 and 5 by 5 matrices can do the job for you. Okay, so clearing the screen once again, and now we're going to start our image processing or playing around with those images. First of all, I'm going to be making a dummy variable b in which I'm going to be storing the image I, so that I don't have to import the image again and again into MATLAB. Now, in order to convolve a two-dimensional image, what I'm going to do is I'm going to write in the function convolve2, which convolves two-dimensional signals. And now what I'm going to write is double and double. These two are the parameters, and the parameters are going to be matrices, obviously, but the matrices have to be in the form of double, because MATLAB does not convolve unsigned integer images that have 0 as their black and 255 as their white. And sadly, our grayscale images are unsigned integer images, which MATLAB calls it as unsigned integer 8. Okay, so I'm going to be converting those unsigned integer matrices and those images into doubles, which I'm simply going to do by writing the image or the matrix in this function of double. Let's say I'm going to move the image a pixel to the right. So I'm going to be convolving B with the matrix that moves the image a pixel to the right. So we have our convolved image B, but it is going to be in a form of double. And in double, we have our images having 0 as black and 1 as white instead of the conventional unsigned integer, in which we have 0 as black and 255 as white. So I'm going to be converting the image into normal grayscale version that we know of, unsigned integer 8 as they call it in MATLAB. And voila, here's our image, moved a pixel to the right. As you can see over here, the small black portion shows that the image was moved a pixel towards the right, increasing a black spot over here. There's a little increment of black spot below over here, but that's because you can call it as noise or anything, because we convolved our image with a 3x3 matrix. If we were to convolve it with a 5x5 matrix, this black area would have reduced significantly. But increasing the size of matrix will increase the demand of computation power for two-dimensional convolution. So 3 or 5x5 is good enough because this area is still pretty much negligible as compared to this one. Okay, so now we're gonna start blurring images because moving them a pixel to the right or to the left basically gives the same effect. So let's just restore I and B, and this time we're going to convolve, we're going to blur, and this time we're going to blur the image. But blurring is not as easy as it looks, because when I do this, you'll see what I actually want to show you. You can clearly see this is the original image, and this image has gotten a little blurred, but it has its brightness increased. The reason is the same Gaussian function that I was talking about. The Gaussian originally has a magnitude of 1, but when we convolve with the matrix that I had for blurring, the matrix was not normalized to be 1. And since it was not normalized, the image did get blurred, but its intensity or its brightness increased. So the brightness increases as you increase the pixel values. For example, if it's 233 and you make it 245, then it will have its increase in brightness. And since convolution is multiplication and addition, and if you add numbers and you keep on adding them, then the brightness will definitely increase, which it has in this case. So the solution to this is you normalize the matrix, and the way to normalize the matrix is that you sum the number of elements inside the matrix. For example, for blur 1 matrix, my summation would be equal to 2. So I'm going to do just that. I'm going to divide blur 1 by 2 and now see the results. Here's a blurred image and here's the original image. You can clearly see that a blur has occurred, and if I am to convolve it with blur 2, which I'm going to do just right now, you'll see the blur will get better. Because the blur 2 matrix has a larger standard deviation of the Gaussian bell curve than blur 1 did. And if you look at it, it really does blur it much better. Talking about the third blur matrix, okay, you can clearly see that the blur has increased significantly because the standard deviation of blur 3 matrix was 1, which was larger than the previous 2 matrices, and so the image has got more blurred than the previous 2 matrices. This is the original image, this is the blurred image, and if you see over here that the edges have gotten smoothened up. The reason for that is because I'm convolving with a Gaussian function, and a Gaussian function actually smoothens the signals, or smoothens everything that it gets convolved with. And getting convolved by the Gaussian function actually smoothens the edges up. That is why you see that these edges have been smoothened up. And in blurring image programs, usually the Gaussian function is used because it gives a better blurring effect than any other matrix, because all you need to do in a Gaussian matrix is that you have to find the proper standard deviation value, and then you just convolve it with that, and then the image just comes out really nicely blurred. So this is how convolution of matrices and images work. And talking about mobile applications such as Instagram, Camtasia or Snapchat, all of them use the same logic of convolving images with the previously stated matrices to create their filters. The lines of codes are same, the convolution method is same. The difference is just in the values in those matrices, and that is what makes their filters differ from each other. It is also a really big thing in system of filter designing, because for any dimensional signal that you choose to process, you have to choose a system with those specific values that will give you the best output. You may know all the logics, but the question is, can you find those special system parameters that will make your output better than the others? That is all. Thank you.